In order to understand all the principle of creating our own sounds, we should first look back at some core concepts. So in this video, I will introduce the basic waveforms, which we will use on synthesizing our own sounds, as well as the way as we can read the representation of those waveforms on diagrams. Seeing a sound wave with our eyes is impossible, so we need a certain graphic diagram that shows us the pattern of changing air pressure over time. We call it a waveform diagram. When a source is expanding and contracting consistently, it is said to be moving in harmonic motion, and the representation we get in the diagram for such a movement is a sine wave. A single isolated sine wave can only be created by an electronic source known to us as the oscillator, but we can see all other waveforms as being thousands or hundreds of sine waves put together. We can read the representation of a waveform in the following way. We have an amplitude axis, which is bipolar, where we see air pressure and silence. We have a time axis, and a curved line that shows the air pressure pattern from compression and rarefaction. This can be represented with one or more cycles. We can also see the wavelength, which is the distance between two adjacent points in two cycles of a waveform. And we can see the frequency, which is the number of cycles per second. The higher the amount of cycles, the higher the frequency, the higher the pitch. The lower the amount of cycles, the lower the frequency, the lower the pitch. It's now time to talk about basic waveforms. For that we need some tools. I have a synthesizer, an instance of Serum, which I'll use its oscillator to generate the waveforms. Then we have a spectrum analyzer, which shows us the frequency content, and we have an oscilloscope, which shows us the waveform. The sine wave is the most basic waveform. It has no harmonics. It has just one tone, which is the fundamental frequency. The fundamental frequency is what gives us the notion of pitch, and we can see all other sounds as being layers of sine waves, but we'll get to that in a moment. Next we have the triangular waveform. It has harmonics above the fundamental. Odd-numbered harmonics where the amplitude exponentially decreases, as we can see on the graph. Then we have the sawtooth waveform, or saw waveform. It contains all the harmonic series, giving it a sense of brightness and richness in relation to the sine wave or the triangular. And then we have the square wave. Like the triangle wave, it contains only the odd-numbered harmonics, only that the amplitude decreases regularly instead of exponentially. These are the basic waveforms, but we still have the pulse waveform, which is a form of square wave, but the difference is that one of the sides is skewed. So that in the square wave, we need to have 50% of the waveform in the positive and 50% in the negative. A pulse wave differs by having one of the sides bigger than the other, which gives it a more nasal tone. In relation to the square. And this is it, but what do we mean by harmonics? Why is this called harmonics? Let me show using a sawtooth waveform, for example. As I said, sawtooth waveform is the most rich of the waveforms because it gives us all this harmonic content, which are all the harmonic series. And what I mean by that is I will just freeze the image. What we mean by harmonics is that all these little spikes here are harmonically related to the fundamental tone, to the fundamental frequency, which is the first harmonic. Being that this second harmonic is twice the frequency of the first, the third harmonic is 3 times the frequency of the fundamental, the fourth harmonic is 4 times, and so on and so on. So they are harmonically related. We could have some inharmonic content, for example, a noise. It means I get all this frequency content which is not harmonically related, therefore it's inharmonic in comparison with this, which is mathematically related to the fundamental. Remember I said we could build all other sounds with sine waves? Well, think about this as being a different sine wave. So if you had a bunch of sine waves with the correct frequency interval and amplitude, you could easily create this sawtooth waveform right here. In the case of the square wave and the triangle wave, which I said contains only the odd harmonics, it's because they only have the harmonic 1, the 3rd, the 5th, the 7th, and the 9th, and so on, so on. Each one of these harmonics is a tiny little sine wave.